This is the lecture on Le Chatelier's principle. We've already talked about how to predict whether a system will shift towards products or towards reactants based on starting conditions by calculating the reaction quotient Q and determining whether Q is larger than K and must get smaller, or if Q is smaller than K and has to get bigger. Le Chatelier's principle is an easy rule to follow that will predict shifts in a system that's already at equilibrium if we make a change to the system. So Le Chatelier's principle states very simply that if a system is already at equilibrium and it's perturbed, just meaning that you make some kind of change to it, right, then the system will shift in the direction that opposes the change, right? And this is in order to reestablish equilibrium after you've made the change. So if we consider a generic reaction equilibrium, A plus B goes to C, right? And you can see that the reaction quotient or equilibrium constant equation is products over reactants. So concentration of C over the concentration of A times concentration of B, right? And we think about, okay, what happens if we perturb this system that's already at equilibrium by increasing the concentration of A? So if we increase the concentration of A, let's think about this from terms of rates, right? What happens when we increase the concentration of a reactant? Well, if more A is added, then the forward rate of reaction becomes faster. And this means that the reaction will shift towards the products because now the forward reaction will be faster than the backwards reaction, right? And it will keep shifting towards products until equilibrium is reestablished and we've returned back to the value of K. Now, as a result of shifting towards the products, we'll get a decrease in both A and B, right, as they get used up, and we'll get an increase in C as it's produced. Now, if we talk about this in terms of Le Chatelier's principle, right, then A was increased. This was the perturbation or the change made to the equilibrium, right? And this causes the equilibrium or the system to shift towards the products in order to oppose the change made. So the opposition would be that A has to be reduced, right? So it has to shift towards the products in order to oppose the increase in A, which is by reducing A. So we can consider another concentration example. Not only could you increase the concentration, but you could also decrease the concentration by removing something from the system. So in this case, we're going to ask, well, what happens if we decide to decrease the concentration of B, right? Well, again, if we look at exactly what's going to happen here, if we decrease the concentration of a reactant, then this is going to decrease the rate of the forward reaction. So now, rather than speeding one of the reactions up, we've actually slowed one of the reactions down. So if we slow down the forward reaction, that means the backwards reaction will be faster than the forward reaction. And so this is going to cause a shift backwards towards the reactants, because now the reverse reaction is going faster than the forward reaction, right? And it'll keep shifting backwards until we reach equilibrium again. Right? If we look at what happens when this backward shift happens, well, shifting backwards causes C to decrease as it gets used up, and we'll be producing more of both A and B. Now, according to Le Chatelier, since we made a decrease in B, the system will shift in order to oppose that change. So by decreasing B, the system shifts towards the reactants in order to oppose that change, which is by increasing B. These examples are pretty simple, but there are other ways we can use equilibrium, Le Chatelier's principle with respect to equilibrium. For example, if we look at an equilibrium involving gases, right, we can actually look at changes in pressure, right? So now I've just added gas states to all of our reactants, A, B, and C, just to imply that they're all gases, right? And if we ask what happens if we decrease the volume of the container by half, right? Well, then we have to think about our gas laws, right? If we decrease the volume of the container by half, right, we you should realize that by Boyle's law, right, the pressure should increase by double, right? And not just the overall pressure, but the pressure of each gas in the reaction should double, right? So the other thing we can tell from rearranging the ideal gas law is that pressure and concentration are proportional, right? And you can think about this: if you squish the particles into a smaller space, you're going to be increasing the concentration of those particles. So by decreasing the volume of the container, what we do is we double the concentration of everything in the container, right? And what this will result in is increasing both the forward and the reverse rate, right? We're increasing the concentration of A and B, which increases the forward rate, but we're also increasing the concentration of C, which increases the reverse rate. The difference is that since we've doubled everything, we're doubling A and B. So the forward reaction is being doubled twice, so times 4. But since we only double the reverse reaction once, it's not going to be moving as fast as the forward reaction. So now the result is that the forward reaction is now moving faster, right? And it's going to shift towards the products. Right, so the result here is by increasing the pressure, right, we decrease A and B as they get used up when this shifts forward, and we increase C, right, as it gets produced. Right. Now, if we think about this from the terms of Le Chatelier's principle, right, we can think about pressure on both sides of the reaction. Since there are 2 moles of gas in the reactants and only 1 mole of gas in the products, that means that there's more pressure on the reactant side, right? If we use up A and B, 2 moles of gas, and we produce C, which is only 1 mole of gas, that'll be a reduction in pressure, right? So we can consider pressure a reactant in this case. So if we put pressure on the reactant side, and now consider what happens when we perturb this equilibrium by increasing the pressure, right? Well, Le Chatelier's principle says that it will shift so that it will oppose that change in pressure. So it shifts towards the products in order to remove moles of gas, and that reduces the pressure. Right, so Le Chatelier's principle works for pressure as well. So the last example that we can use Le Chatelier's principle for is changes in temperature, right? So the question here is, what happens if we increase the temperature for this reaction, right? As we know, the value of the equilibrium constant is only valid for one temperature. If we change the temperature, then the value of the equilibrium constant K also changes, right? So that would mean that we now have to shift the equilibrium in order to move it towards the new value of K after we change the temperature. Now, which way this reaction will shift with an increase in temperature actually depends on whether or not the reaction is endothermic or if it's exothermic, right? An increase in temperature will increase both rates of reaction. An increase in temperature always increases rates of reaction, right? But the forward and the reverse rates won't increase proportionally. They won't increase by the same amount. They'll both increase, but just not by the same amount. And this is why K changes. The ratio of the forward and reverse rates actually changes when you change the temperature. So let's look at the potential energy profiles of exothermic versus endothermic reactions. On the left, we have an endothermic reaction. We can see that the forward reaction's activation energy is larger than the reverse reaction's activation energy, right? And it's the activation energy which determines how fast the reaction goes. And then if we flip that reaction around, we get an exothermic reaction on the right, and now we get the reverse scenario. The activation energy of the forward reaction is smaller than the activation energy of the reverse reaction. As a result, right, although the temperature will increase both reactions, right, it has a greater effect on the rate of the reaction with a larger activation energy. Right? So for the endothermic reaction, increasing the temperature will make the forward reaction faster by more than it makes the reverse reaction faster. And conversely, with the exothermic reaction, the reverse reaction with the larger activation energy will get faster more than the forward reaction for the exothermic reaction. So this is all very complicated, and it can take quite a while to work your way through what's going to happen when we increase the temperature, right? So Le Chatelier's principle actually makes this a lot simpler, right? We know that if this was an endothermic reaction, so let's say it's endothermic, then the forward rate will increase more than the reverse rate. That's simple enough to understand. That means that it's going to shift forward because the forward rate is now going faster than the reverse rate. And so what happens when we shift forward? Well, reactants get used up and products get produced, right? That makes sense. But the easy way to determine all of this for Le Chatelier's principle is to consider whether an endothermic reaction, an exothermic reaction, absorb heat or release heat, right? In this case, if we're considering this to be an endothermic reaction, right, then the endothermic reaction will absorb heat. That means that heat is getting used up, right, or can be considered a reactant. So if we add heat to the reactant side, right, this describes an endothermic reaction. Heat gets used up, right? Now, if we say, okay, well, the perturbation we're making to this equilibrium is that we're increasing the temperature. So we can consider this an increase in heat. Well, Le Chatelier's principle says that the system will shift in the direction that will oppose that change. Well, that means it has to shift forward so that you use heat up, and it'll bring the heat, the temperature back down, right? So Le Chatelier's principle works again for temperature. So the types of changes that we can use for Le Chatelier's principle to predict for changes in a system at equilibrium are changes in concentration, changes in pressure, and changes in temperature. Right?